All right, let's go ahead and get started. Just want to remind you, we have exam 3 on Wednesday. Yep. So exam 3 is covering chapter 9. Now, we didn't do the real gas laws stuff at the end. You do need to know what we talked about with heavier gases being slower and lighter gases being faster, but none of the calculations that go along with it, the root mean square stuff that's in there, you can ignore that. I would just ask you a qualitative question. Here's two gases, here's their masses, which one's faster? Um, the stoichiometry stuff at the end of chapter 4, where we can include mass, because our last test only had solutions. So we can include mass. We can also include gases now that we can find moles for gases. And then for energy, just section 5.1 and 5.2, and we will go over 5.3 starting Friday. The end of the semester is quickly approaching. Next week will be a full week of classes, and then the following week is Thanksgiving. And then after that, we have 1 week of classes. So in that time, we need to finish with Hess's law and then talk about the electronic structure of atoms and stuff like that. So got a lot to do in the next couple of weeks. So that's kind of what's on board for the future. I had this posted last week, but active chemistry homework 17 and 18, one is over gas laws, one is over energy. Make sure you're getting those done. I do assign those so that you have practice before the exam. I'm not just a sadist, I promise. So any questions about stuff that's coming up? All right. So I wanted to look at a couple of things from the quiz that people had some difficulty with. The questions were randomized in 2 ways. So one way was that not everybody had the same questions. You had questions about the same topics, but you may have seen one kind of question about the conservation of energy and somebody else got a different kind of question about conservation of energy. So one of the questions that we had about conservation of energy asked about which can be said about the energy of the system. And a lot of people were confusing the energy of the system with the energy of the universe. The system can change energy. So that's why we call it either exothermic or endothermic, is because it's either gaining or losing energy. And a lot of people said, oh, the system can't gain or lose energy. It can, but whatever amount that is, it's equal to an opposite of the surroundings. It is the universe that does not change energy. So if that was one that you got wrong, that's kind of the rationale behind that. There was another question that asked about heat capacities of several materials. And I don't remember exactly what the heat capacities were, but I'm going to guess. So C for water, I do know is 4.184. C for glass, I think was around like 1.8. C for aluminum was around 0.9. And C for copper was around 34 or 4.3. And so the question asks, if I have equal amounts of these, because it's per gram, so if I have the same mass of water, same mass of glass, same mass of aluminum, same mass of copper out on a bright sunny day, so they're absorbing sunlight and presumably temperature from the day, which one will get hot the fastest? So because this has a high heat capacity, think of as being how much it can hold. This can hold a lot of energy before it's going to change temperature. So let's say I put in 5 joules of energy into each of these. What that means is this one will have enough energy to barely go 1 degree up in temperature, right? Because it takes 4 joules to get it to go up 1 degree. So it's not even going to go up 2 degrees. This one will probably go 2.5 degrees warmer, okay? Because it only takes 1.8 joules to go up the 1st degree. Another 1.8 joules will get it to the 2nd degree, and then you got a little left over to get to 5. So this one will go up about 2 degrees. Your aluminum is probably going to go up a little over 5 degrees. So this is very close to 1. So 1 joule would make it go up 1 degree. So 5 joules would make it go up 5 degrees. And then following that trend, the copper here is going to end up going up about 15, 16 degrees. Okay. So this is why metal in the summertime can be very hot. When I was a kid, playgrounds had metal playground equipment, and you go down the slide and you would have to have like your legs in the air, because if you went down the slide wearing your shorts, then you would burn your legs on the slide. And now they make it out of plastic, and you think, oh gosh, that plastic gets so hot. It is nothing like how metal used to get very hot in the summer. Okay, so most people picked water that got this wrong, thinking, oh, it has a high heat capacity. But the high heat capacity means that it takes a lot of energy to change the temperature. So water kind of keeps things closer to the same temperature. Okay, let's see. The other two I wanted to go over involve calculations. So I'm going to switch over to those. If you have specific things you want me to go over about the quiz, you went back and you looked through and you're like, I don't know why that's wrong. Let me know and I will try to address those. I might post those on Canvas so everybody can kind of see, the explanation for it. Or if it's something specific to the way you answered it, then I might respond to you individually. All right. So can anybody think of another question they had that they were like, I got this wrong, but I don't know why it's wrong? Okay. I do have to say, with regards to the online quiz, I was disappointed that I have evidence of a bit of cheating that was going on. And I am deciding what I'm going to do about that. And I want to let you know that one of the options I'm considering is just using this as the dropped quiz for everybody. I haven't decided what I'm going to do yet. But I'm very disappointed that, especially since you went through and knew exactly what was and was not allowed, people cheated anyway. Okay. So first thing that I want to talk about is representations of conservation of energy, and then I'm going to use that to address the problem. Why is this piece of chalk still in existence? Okay, so we know that conservation of energy means that the entire universe's energy stays the same. If we think about a pie graph, for a pie graph, it represents the percentage of something. What percent of the whole is each wedge? So the pie graph is going to be 100% of the energy of the universe. All right, so we can't get any more than what's inside this circle, right? What's inside this circle is 100%, and I can't like take a chunk out of the circle. This is everything, and it's going to stay the same. Now, for our purposes, we break it up into two portions, and since most of the universe is not part of our system, I'm going to make the system very small. And the surroundings very large, okay? So when we have a reaction, we can change the size of this wedge. We can make it smaller or we can make it larger. But in order to change the size of this wedge, we have to change the size of everything else, right? And we have to change it by the same amount. Okay, so I have two possibilities. I could have try to make this roughly the same size here. That one's a little bit too big. So one possibility is that this wedge gets bigger. I'm just going to make it dramatically bigger. Oops, it's not going to the middle. Let's do that. Okay. Okay, so more energy is in the system, right? Less than is in the surroundings. Does that make sense? Okay, so what would I say this process is if I got more energy into the system? Is that going to be endothermic or exothermic? Endothermic, because the system is gaining energy. So if I wanted to show exothermic, then I would need to show that the surroundings gained more of the pie and the system got less of the pie. So I'm going to have a thinner wedge for my system. Okay, so sometimes on tests, just to test the concept of conservation of energy, I might give you a pie graph like this and say, well, what would the pie graph look like for an exothermic reaction afterwards? So I could have these two things, but I might also show you a reaction where the circle gets bigger or the circle gets smaller. The size of the circle does not affect anything because the entire circle represents the entire energy of the universe, and that stays the same. So all we're looking at is the portion that is part of the system and the portion that is part of the surroundings. Okay. Another way that I sometimes ask this on tests is using a bar graph. And this I might use if I were going to show a very specific system. I mean, I could write system and surroundings there. But I'm going to show this using our calorimeter so I can kind of connect it to the problem that we're going to do. So if I were to show the energy of the universe, it would like be a bar that would go from here way up into the sky. Total energy of the universe is just huge. But if I have, some of you had the example of a hot piece of metal being dropped into water on your quiz. So this was, let me basically draw my calorimeter here. Kind of looks like a drink, but it's not. A little bulb at the end. And then here's my piece of metal. And then I have water. Okay. The metal is the system. So it was hot at the beginning. It has some amount of energy. So I'm going to call this the metal. The water also had some energy. Now the water is less hot. So the water's starting out at room temperature, but there's more of it. There's this little chunk of metal, but there's a whole bunch of water. So maybe they're roughly the same. Let's try to make those flat so we can kind of see what's going on there. Okay, so this is the water. And then we have our calorimeter. So this is the styrofoam cup that's kind of keeping the heat in there. Now it's going to get a little bit warm. The thermometer has to absorb some energy in order for the temperature to rise. So I'm just going to call this the energy of the calorimeter. It doesn't have a lot of energy because it doesn't weigh very much, but it's got some energy. So this is before. Okay. So, and describe what's happening. Hot piece of metal dropped in room temp. Okay, so this is before, then after, we can think about what happens to the different energy. So what's going to happen to the temperature of the metal? It was near 100 degrees, and then it gets dropped in room temperature water, and then what happens? It's going to cool down. So as it cools down, is energy leaving the metal or going into the metal? Leaving the metal. So the metal, instead of drawing it up here, this is its former height, we're going to have the metal lower, some amount lower. It goes down in energy, right? Now, what happens to the water? It's going to increase in energy, right? So the water was roughly the same height in the before, but it's going to go up in energy. Okay, I'm going to keep my H2O. Now it's going to go almost up as much as the metal goes down, but a little bit of that energy is going to go into the calorimeter. So we had our calorimeter there before. That's going to go up just a little bit. It doesn't gain a whole lot of energy, which is why a lot of times we just ignore it. All right, so why do I draw these graphs? Well, what we want to think about is when we're doing our calculations, this part is our surroundings, and this is our system. Okay, so what that tells us is that the Q of the surroundings, which is the water and the calorimeter, is equal to, is it equal to the Q of the metal? A little bit wrong there. What's wrong? It's the negative of Q. So this was one mistake that some people made. They forgot to make it negative, so they ended up with the negative heat capacity. Okay, so the metal is our system.
So you can't have a negative heat capacity.
No, because remember, the heat capacity means I put energy in and the temperature goes up. How much energy does it take to make the temperature go up? So a negative heat capacity would mean I put energy in and the temperature went down, which doesn't make sense, right? Okay, so let's do some actual data. Okay, so we talked about this being a piece of metal. We're going to say this metal starts at 97.4 degrees Celsius and it weighs 9.7 grams. And the water that we put it in, right before we put it in, we measured the temperature at 19.2 degrees Celsius. Okay. The amount of water was 51.7 grams. And then as the metal sat in there, and when you do this in lab, you'll have a stirrer to make sure that the water's mixing well so you don't have hot spots and cold spots in the water. They reach a final temperature of 21 degrees Celsius. Sometimes we call that thermal equilibrium. So if you see thermal equilibrium, that means that is the final temperature for both the system and the surroundings. Okay. So we need to find Q of the water and the heat capacity of the metal. So for some of you, I asked you a question where you had to find Q of water, and some of you, I asked you to find the heat capacity of the metal. So we know, and this was given to you, Q is equal to MC delta T. But what you want to remember is that this Q has to be for the same thing that you're finding the mass of and the C and the delta T. So I can't use the mass of the water and the change of temperature of the metal together. If I'm doing Q of water, I have to use the mass of water, C of water, delta T of water, right? So for water, we're going to have the mass of the water was the 51.7 grams. C is given right here, 4.184 joules per gram degree Celsius. And the change in temperature is final minus initial. Is final minus initial. So our final was 21. Minus the initial was 19.2. Okay. And this is where you have to pay attention that I'm using the initial for the water. The water's initial was 19.2, but the metals was not. So make sure every one of these numbers has to do with water. Okay. When you have parentheses, that's the very first thing in order of operations. You may have learned, please excuse my dear Aunt Sally, or some other mnemonic device. P is parentheses. That's the first thing that you do, and this works out to 1.8 degrees Celsius. Now, if you want to convert it to Kelvin, because sometimes you'll see this written as Kelvin, that's okay, but you have to add 273 to both of these, and you will still end up with 1.8. So you will probably make fewer mistakes if you just leave it in Celsius. Okay, so then we multiply those across, and I recommend you do this on your calculator. How many sig figs should the final answer have? Oh, I'm hearing 5 and 3. 2, 9, all kinds of things. 2. Yeah. So each number has 3 or more, but when we do this in the parentheses, that's going to limit us to 2. Okay. So that makes it a little bit smaller. So I got 389, but it basically works out to 390 joules. Because we have to limit it to 2. Okay, so that answers our first question. What is Q of the water? Okay, then the second question is, what is C of the metal? So 2 things we have to remember is that C is specific heat capacity. So think of the C as being the capacity. Q is heat. Okay, so in that question, I told you Q of water, or the heat of the water, was 390. So then what do you have to do to make Q of the metal? How are they related? They're negatives of one another. So the surroundings was 390. And so the negative of that is going to be negative 390. Okay, so Q of the metal is negative 390. All right. The other thing is we are going to solve for C. So we can rearrange this equation and say that C is equal to Q divided by M delta T. Now I had a number of people on the quiz dividing upside down. So they got the two things on either side of the equal sign, and instead of moving this one over here, they moved this one over here. So be really careful about how you do those things. And this is where having a sense of what the number should be is helpful. So I erased it, but based on the numbers for copper and for aluminum, what would I expect about C? Should it be bigger than water or smaller than water? Definitely smaller, and it should probably be less than 1. So if I'm getting a really big number, or even just a number that's bigger than 1, I might want to go back and check my calculations. Now, because of the way that on the quiz I did the second kind of randomization is I just had it generate numbers to plug in. Everybody who did the same calculation had different numbers. You may have ended up with a C greater than 1, but it shouldn't have been a lot greater than 1. Okay, so let's plug this in. We're going to have C of the metal is equal to negative 390 divided by the mass of the metal is 9.7 grams. This is joules. And then our temperature, are we going to do the 97 minus the 21 or the 21 minus the 97? 21 minus the 97. So the final goes first, minus 97.4. Okay, and again, since this is in parentheses, this is also in parentheses, but there's not a calculation there. This is in parentheses, so we have to do that calculation first. All right. Let's see, calculator. All right, because this is small minus large, this will be negative, but this is also negative. So those two negatives cancel each other out, right? And that's how I end up with a positive heat capacity. So turn this just a little bit. I get 0.49 and none of my units cancel. So it is joules per gram degree Celsius, and that is appropriate. Okay, does that seem like a reasonable heat capacity for a metal? Less than 1? Yeah, and it's positive. Okay, so that's how we do those calculations. Now, what I want to do for the last part of class is look at what if instead of just a physically changing temperature thing, we do a chemical reaction.
So we don't have any time.
So I'm sorry.
Well, a question like that, we have any time.
Yeah, I mean, that was on your quiz. So, I mean, on your quiz, I did break it into 2 parts. On your exam, I may put it all together. And if you look at your exams, I do have it on there. And the one I'm about to do is also from an old exam. But if you look, I will provide you with some scaffolding where I will say, okay, what is the mass of the metal? What is the mass of the water? What is the heat capacity of this? What is the heat capacity of this? Now, sometimes you will have to put in, I don't know, because that's what the question's asking for. But I will try to provide some scaffolding. This is another type of problem that's very common. So you can look for YouTube videos or Google search how to do these kinds of calculations, and you will find any number of people willing to go through example problems of this. So if this is intimidating, I recommend that you spend a little bit of time looking at videos of this kind of thing between now and the exam. I will try to provide a couple of links of those, and sometimes people tell me, oh, I found this great video, and I'm like, please send me that video so I can share it with other people. And so far I haven't gotten it. You guys know who you are, who I've said that to, so send me your video links. All right, so Okay, so in this process over here, we have energy coming from energy transfer. So the energy is going from one, we call it a body in chemistry, one substance to another. It's going from the metal to the water. But it's basically that kinetic energy of heat. It's a temperature change. In a chemical reaction, it is transformation. It is going from one kind of energy to another. So everything's going to start out at room temperature, and then we're going to do a chemical reaction, and the temperature will rise. So we're not getting hot mixing with cold. We're getting a change from chemical energy into heat energy. So why does this happen? Some chemical bonds are more stable than others. And so as you do a chemical reaction, generally what's preferred is to form the more stable bonds. And so that tends to form exothermic reactions, but there are reasons why sometimes we have endothermic reactions. And so this is going to be an endothermic one. But basically we are taking chemical potential energy and exchanging it with heat energy. So we're either using heat energy to make less stable products, or we're using the energy that results from making more stable products to generate heat. The easiest way to make these measurements for chemical reactions is with aqueous solutions. So in aqueous solutions, we know aqueous means what substance? Water. So in aqueous solutions, water is the surroundings. Okay, now when I did the bar graph over here, we had the calorimeter on here, and I said the change wasn't very much. It is part of the surroundings, but I also told you that in this class, we're going to pretend like it just doesn't really absorb anything, so that the water is doing all of the surroundings. When you get to lab, you're going to make a slight adjustment for the calorimeter. So if it seems a little bit different in lab, that's why. That's a better way to make that measurement. But I'm trying to keep things simple for you. Okay, so water is the surroundings. Now we can have reactions under all kinds of conditions. So most of the time we do them in the open air. So the pressure is constant, right? We have the air pressure. You could do it in a closed container. We call that kind of a calorimeter a bomb calorimeter, because if you have an explosion, then it contains what's kind of like a bomb. Dr. Fraley may show you our bomb calorimeter in lab this week or next week, but we're going to always assume that we're using constant pressure. So at constant pressure, Q of the reaction is equal to what we call enthalpy. And enthalpy has a somewhat confusing symbol, H. Now, because it's a reaction, which is a process, there's a before and after, we look at the change in enthalpy. Okay, so we say delta H. So that triangle means the amount of change in energy, the potential energy of our chemicals. So if we have a chemical reaction that is A plus B going to C plus D, just generic, then the H, the enthalpy of A and B, the potential of those bonds, is different than the potential of the bonds for C and D. Now, if they're very similar, we're not really going to notice much going on. Okay, but if they're very different, then the temperature of the surroundings can change quite a bit. Okay, so Q of the reaction is Q of the system. The system is the reaction. But because it's aqueous, all of those chemicals, A and B and C and D, are floating around in water. And as they react and produce or absorb energy, the water is going to respond to that, okay? So Q of the water is Q of the surroundings. So we can say Q of the reaction is the negative of Q of the water. Now, one thing that I should add over here, this delta H, is Q per mole. Okay, so usually when we do something in lab, it's like we found the heat this time for this set of chemicals, this amount, this is how much heat was produced. Delta H generalizes that to say, well, if I had any number, can I figure it out by saying the heat per mole? So we can say delta H of a reaction is equal to Q of the reaction over N. And what does N stand for? Moles. Okay. Now, this is a weird sort of thing to wrap your head around, but how do you say moles of a reaction? Are we counting up each of the reactants and the products? Do we account for the coefficients if there are any? So 1 mole of a reaction is as it is written. If this happens with 1A, 1B, 1C, and 1D, then that is 1 mole of reaction, okay? What gets weird is if the reaction were, say, 2A, 3B forms 2C and 4D, this would still be 1 mole of reaction, okay? As it is written, if 2 A's react with 3 B's, that is 1 mole of reaction. I know it's weird. That's the way they do it. This is why it is important to put your balanced equations in the lowest ratio. That's why if you've had something taken off on a quiz or a test for balancing because you had 4, 4, 2, 4, because energy-wise, that's not the same thing as 2, 2, 1, 2. We want to have it in the lowest ratio. Okay, so let's do an example. Do this fast. All right, our reaction is going to be barium hydroxide, aqueous, plus ammonium chloride, also aqueous, forming barium chloride plus ammonia plus water. And we are going to have 50 milliliters of each of these. Give ourselves 3 sig figs here, 50.0. We were pretty precise in measuring it. And this one, because it's a solution, was 1.5 molar, and this one was 3.00 molar. And then the total mass of the solution is equal to 108.5 grams. All right, for our purposes, we're going to keep it simple, and we're just going to assume that this entire mass is the mass of the water. There is a way to calculate what mass is those chemicals and pull that out. We're not going to bother with that. But we do need to know how many moles we have, okay? Do we have an entire mole of barium hydroxide so that we would have 1 mole of the reaction? Or do we have something less than that or more than that? So how do I find moles with a solution? It's going way back to chapter 4. Moles for a solution is equal to, remember this is molarity is moles per liter. Molarity times liters. Molarity times the volume, and I'm going to put a little L here, the volume in liters. Okay, so if I multiply these two, and then I have to divide by 1,000 because that's in milliliters, then I end up with 0.075 moles. Oh. Over here, I'm going to end up with 0.150 mole. Okay, so these are in the right ratio. This is twice this. So I don't have 1 whole mole. I have 0.075 moles of reaction. Okay. So that's figuring out the mole part in here. N. Now I want to find Q. So Q of the water will equal the mass of the water times the heat capacity of the water times the change in temperature of the water. Now in this case, the change in temperature of the water is also the change in temperature of the reactants. So we're not going to have 2 different things we're going to look at. I haven't given you that information yet, which you will need. So our temperature goes from T1 is 18.7, a cool room, to T2 is 10.7 degrees Celsius. So it gets chilly. Not frozen, but chilly. So Q of the water is going to be the mass of the water, we said was 108.5. C of water, I will always provide you. Delta T, which goes first, 10 or 18? Final minus initial, so 10 is going to go first. Okay, so this is going to give us 8.7 degrees. That's going to limit our final number to just 2 significant figures. Okay. And is this result going to be positive or negative? It's going to be negative because this is negative, right? All right, so 8.5 times 4 times negative 8.7. These tend to be pretty big numbers, so I get negative 3949.5, but I only get to keep 2 of those. So I'm going to say negative 3900, right? So if I have a big number that I have to limit to 2 sig figs, instead of just deleting the 4 and the 9, I'm going to change them to zeros, but then I leave off the decimal. The decimal would say they're significant. These are not significant. So I'm just going to put the decimal. So is this the Q I'm going to plug in over here? It's going to be positive. Very good. Because this is water, which is the surroundings. Q of the reaction is going to be the opposite. So Q of the reaction equals positive 3,900 divided by, this is 1 mole of what's happening here. So 0.075 mole. And we get a positive 53,000 joules, or positive 53 kilojoules. Chemical reactions tend to be in the kilojoules. Okay. So next week in lab, this is basically what you'll be doing. Your reaction will be a warming reaction instead of a cooling one, but that's what you'll do. All right, I will see you all Wednesday for exam.